Okay. In this segment, we want to look at how you can determine the parametric equations of a curve if you're given only a verbal description. So obviously I have some images here as well. The curve that we're interested in today is called a cycloid. Okay, so for our cycloid, let's say a wheel of fixed radius capital R rolls along the x-axis. At a point on the edge of the wheel, we're going to call this point P. Point P starts at the origin, and the cycloid is what you get if you track the movements of point P as the wheel rolls along the x-axis. So, in order to determine the parametric equations for this curve, it's helpful to decompose the motion of point P into two parts. Okay, so let's think about how we're going to do that. So we're going to have x of t, and x of t is going to give the horizontal position of point P, and y of t is going to give the vertical position of point P. And y of t and x of t will be measured from the origin. Okay? So, all right, here we go. So I've labeled some things in the diagram here. Again, our goal is a set of parametric equations for the position of point P, which will give us the formula for the cycloid. And again, we're looking for x of t and y of t. X is the horizontal position of point P from the origin, y is the vertical position of point P from the origin, and t would be, you can see I have t labeled in the center of the wheel here. T would be the rotation of the wheel in radians starting from the starting point, from the origin, okay? Okay, so let's think about what's going on here. Now our goal is an equation for x of t, an equation for y of t. All right, so let's start with x of t. What do I know about x? Well, I know that if point P started at the origin and rolled to the right, okay, then this arc on the circle must be equal to the distance, horizontal distance traveled. Or in other words, I could say that line segment OB is equal in length to arc PB. And that's the distance the wheel has traveled so far into this point where you see P where it is now. Or since point P was at the origin. Okay. Now, what do we know about these two lengths? Well, looking at my diagram and looking at the things that I've labeled, I can see that line segment OB is equal to, let me get rid of that. Line segment OB is equal to length X plus line segment AB. And if you look at, now remember, we're trying to define X and Y in terms of T. That is our goal. X and Y in terms of T. So I want to relate things to t. So first I'm going to say that if you look at my picture, segment AB is congruent to segment PD. So I can now say that OB must then equal X plus segment PD. Okay, now let's draw a triangle, let's draw a diagram of this triangle in here in the center. And let's blow that up so we can use that in our coming up with these equations. So this triangle, which is the triangle from inside the circle, which I'll call triangle PCR, has hypotenuse of length r, that's a radius of the triangle, and then the angle here is angle t in radians. So this, oh, I've labeled this incorrectly. This is a P down here, triangle PCD. Okay, so segment PD, which I've marked in both these places, segment PD, well, I can write a sine function for that. Now remember, capital R is a constant. I can say that the sine of t is PD over length r. And I'm going to plug that in for PD right here. So now I have that length OB equals X plus R sine t, where capital R is a fixed value for the length of the radius of the circle. Okay, now I'm going to go on to the second length we're talking about, which is length PB. So what do I know about length PB? PB is an arc length. I'll come over here. Oops. PB is an arc length. And I know that arc length, oops, not BB, PB, is some angle over 2 pi times circumference, or times 2 pi r, which is a fraction of the circumference, which really means it's going to be the angle times the radius. But I know the angle that we're talking about, the angle, the central angle corresponding to that arc, we are calling angle T. So now I have these two quantities. I have OB and I have PB, arc length PB, line segment OB and arc length PB, and they must be equal to each other. So, therefore, I get that X plus R sine t must equal little t times r. Or in other words, let's isolate x. X equals tr minus r sine t. And how you see this written more often than not is with the r factored out. R t minus sine t. Okay, what about the y value? So now if we go back to the picture, we know that y, y equals line segment CB minus line segment CD. Well, look at this triangle over here on the right side. And I can write a cosine function involving line segment CD. And that would be the cosine, well, first of all, CB, this is R. Line segment CB is the radius of that circle, so that's just capital R. And now, using this triangle way over here on the right, I can say that the cosine of T is CD over R. And that means CD is R cosine T. And that gives me the Y formula for the parametrized version of this curve. So again, I'm going to factor out the R, and I get 1 minus cosine T. And here we have, here I have the parametric equations to describe my cycloid. But we're going to do a little bit of work to confirm this. Okay. So how can I confirm that those equations actually give me the cycloid? So let's look at first derivative behavior. So let me write them up here. X of t is okay. So these are the equations that we came up with to represent this cycloid. Okay. So let's confirm that the equations support the critical features of this graph. So let's start with first derivative behavior. So the slope here is going to be dy dt over dx dt. The derivative, r is a constant, so it's just a multiplier. So the derivative of y is going to be r times negative sine t, or just r sine t. And the derivative of the denominator is going to be r, and then the derivative of what's in the parentheses is 1 minus cosine t. R is a non-negative, R is a positive constant because it represents the radius of the circle, which is not negative or 0. So I can just cancel that out and say that the first derivative is sine t over 1 minus cosine t. Okay, so what do we know here? Well, first of all, I know that we have the tangent line is horizontal when the slope is 0. Okay, so that means when sine t equals 0, and that means when the denominator is not 0. Okay, well, when is sine t 0? So this would be multiples of pi. And when is cosine t equal, well, when is cosine t equal to 1? Cosine t equals 1. Because we want to eliminate all of those values. So that cosine t is 1 at 2 pi n. So even multiples of pi n. So, 0, 2 pi, and so on. So that means that the horizontal tangent lines occur when t is pi plus 2 pi n, or odd multiples of pi. So like negative 5 pi, negative 3 pi, and so on. Negative pi, 1 pi, 3 pi. Okay, odd multiples of pi. Well, where does that occur? So if you think about what's happening, if point P started at the origin, then the circle has to roll its whole circumference before point P comes back to the x-axis, okay? And the circumference is 2 pi r, where r is the radius. So that means this distance is 2 pi r. This distance is 4 pi r, and so on. This is 6 pi r. Oops, these should be capital R's. I apologize. R, because that is a fixed value. And this would be pi r, 3 pi r, and so on. So you can see that at these odd multiples of t, well, what is x? X is x of, I'll do the positive ones. X of pi is r pi minus 0. So that's pi r. Well, that corresponds to this point on the curve, and you can see that the tangent line is horizontal. Or x of 3 pi corresponds to r 3 pi minus 0. And so on. You can see the pattern. So we have confirmed that we have horizontal tangent lines at all of the points where t is an odd multiple of pi. And then I'll also go ahead and just confirm when the slope is undefined, okay? So in this case, the slope is undefined. We already found the values when, let's go back up here, when cosine t equals 1, and we found those to be even multiples of pi n, okay? And if you look at those points, well, what's going on there? What is x of 0? Well, it's 0. X of 2 pi is r 2 pi minus 0, or 2 pi r. Well, let's look at those points on the graph. That's right here. These are the corners, or I'm sorry, cusps that you see on the graph. And you can see in those places, the tangent line is vertical. So the slope of the tangent line is undefined, or the derivative is undefined. Okay. How can we confirm whether that's a cusp or a corner? Well, we can go one extra step to confirm that this is a cusp to actually figure out what the slope is. Okay. So let's pick what's going on here. So let's look at the slope of the tangent line around 0, around t is 0, which is at the point at the origin. So if I say the slope is undefined there, but I'm going to say the slope is undefined because we have a left and a right-hand slope. One is positive, one is negative. We can see those are not equal. But I can also look with more precision and say the limit as t approaches 0 of the slope, well, that's 0 over 0. So now I can L'Hopital that, apply L'Hopital's rule, and I can say that, because I have 0 over 0, that the limit as t approaches 0 of cosine t over sine t, well, that's the limit as t approaches 0 of cotangent of t. Okay. And now, if you think about what the graph of the cotangent function looks like, it looks like this. Okay. And let's think about what's going on around 0. Okay. So on the left-hand side, we have that the limit as t approaches 0 from the left of that graph, running out of room here, that's negative infinity. This is down here I'm talking about on the left-hand side. The limit as t approaches 0 from the left is negative infinity. And on the other side, now in purple, the limit as t approaches 0 from the right of that graph is positive infinity. And that's the definition of a cusp. On one side, the slope of the tangent line is approaching negative infinity. On the other side, the slope of the tangent line is approaching positive infinity.